Now come on this lecture number 14, which is the last lecture of this module as well, of the module number 2, that is the equipment and stability constraints in the system operation. In the lecture number 13 we saw the half bifurcation, which is a dynamic bifurcation, and in this lecture we will see other bifurcations, dynamic bifurcations, and how we can improve the voltage and stability, what are the various methods or you can say measures, and along with also one example with the placements of a static VAR compensator, how it can improve the dynamic as well as the static voltage instability of the system. So other dynamic bifurcations are period doubling bifurcation, it is also called the PDB. This emerges out of stable periodic orbit. The original periodic orbit becomes unstable and the new stable periodic orbits of twice time period emerges out. Means, for example, if you can see here, if you have something here, this is your coming, this is the stable, and from here, this here the period is, let's suppose T1, and it is a stable one, and suddenly if it is going to be stable here and it is your 2T1, and another here the original which was going, it is now unstable. So it is your unstable, and it is emerges out another, that is a twice of the period of this T1, and that is stable, then it is called the period doubling bifurcation. So the new stable periodic orbit of the twice time period is emerging. So this is called your periodic doubling here. Now the torus bifurcation, this also emerges out of stable periodic orbit. The original periodic orbit becomes unstable, and the new stable periodic orbits of the time period, which is fraction of earlier periodic orbit, emerges out. So this torus and the periodic doubling, here is the period doubled. As I said, here it is a period is T1, now it becomes T2 and it becomes unstable. But in the torus, it is your, if it is a T1 and it is stable, and then it is your, this becomes unstable, and your stable here is a fraction of, let's suppose, T1 over some factor n, and we are having another time period. So it is called the torus bifurcation. The cyclic fold bifurcation, this bifurcation takes place when stable periodic orbit folds back and becomes unstable or vice versa. So here you can say the cyclic fold, you can say it is coming here and then it is going back, means folding. Just you can say here is stable, now it is become unstable. So this bifurcation takes place when a stable periodic orbit folds back and become unstable. So it is becomes unstable here. So it is called cyclic fold. Chaos, both PDB and the TRB acts as a gateway to chaos. The multiple emergence of the periodic orbits of the different time periods results in seemingly random behavior and the oscillations, and that leads to the chaos. So the random behavior leads to the chaos, and it is not, we cannot able to determine the behavior of the system, and that is called the chaos of the system. Now all these dynamic and static bifurcations, if you can see here in one diagram, so this is a typical bifurcation diagram. First I explained the saddle node bifurcation point, which is here, and that I am trying to give you in some plate. So this is your real power, here it is your voltage, that is X vector, and this point is your saddle node bifurcation, because here it is your stable and this is your unstable. So it is the point where stable and unstable are meeting, and this is notch point or saddle node bifurcation, which I explained. Now the half bifurcation, as I said, it comes earlier, where at this point, as I said, this Jacobian becomes singular, but here the Jacobian, before this Jacobian is not singular, and there is a possibility that the two eigen, or you can say pair of eigenvalue, becomes complex conjugate, means the real part will be 0, and that can here, let's suppose, is HB, that is here. So again I explained the two half bifurcation. HB is half bifurcation, one is your subcritical, another is your supercritical, and the in between it is called your HB window in this one. So this is your subcritical occurs before your supercritical, because here it is surrounded, unstable is surrounded by stable point, here unstable point is surrounded by stable one. So this is called your half bifurcation window. Now if you are again here, this half bifurcation, as said, this is unstable and it is folding, going back, and now it becomes suddenly stable. So it is called your cyclic fold bifurcation, which just now I explained here. So this point is called your cyclic fold bifurcation. So it was unstable and now it is folding back, and here it is stable now. Now in the periodic doubling bifurcation, as I said, it emerges out from the stable. Here this is stable, and now the frequency becomes double, or in the torus it is a fraction. So here it is original becomes unstable, and then here it is somewhere, and this point is called the chaos. So there is so many oscillations and other things. System is not defined here. This is, you can say, chaos of the system. And finally here you can say this is your supercritical and point, half bifurcation point. So if a periodic orbit or chaotic oscillation grows and touches unstable fixed point region, the voltage collapse may take place due to the boundary crisis. So in this I want to say that if a periodic orbit or chaotic oscillation grows here and touches the unstable fixed point here in this region, then voltage collapse may take place due to the boundary crisis. The chaotic oscillations introduce additional harmonics into the system, that is not desirable. This half bifurcation window and thus dynamic bifurcation can be eliminated with use of proper facts controller in the system. Means we can eliminate even though this half bifurcation at all by using the facts controller, and we will see application of static work compensator, how it can improve your dynamic stability. Here if you can put, then this can be, the window can be eliminated, and then we can load your system up to the SNB, that is a singular node bifurcation point. Now here the lot of people are doing the research in these areas for the various purpose. First, normally they go for the identification of the weak buses, and therefore they form the voltage control area. The voltage control area is nothing but where we want to put the reactive power source minimum that benefit maximum to the system. So we form the voltage control areas, means we are putting reactive power source somewhere that area is benefited much, so that is called one area. As you know, the reactive power is a local phenomena, however the real power injection etc. is your global phenomena, because if you are injecting real power at one point, it is changing the frequency of whole system. However, if you are changing the reactive power, you are injecting or absorbing reactive power, the voltage is change is localized one. So the formation of the voltage control area, there are a lot of works are already existing in the system, but still some more simple and the reliable methods are required. Another challenge is the voltage stability constraint security analysis. Normally people go for the security analysis, means as you know the security is much demanding than your voltage stability as well. So we can add some more constraints in the security analysis, and then we can use the voltage stability constraints, and then we can analyze. Now if you are adding the voltage stability constraints, if you are adding the dynamic constraints, then the system becomes very complex, and getting solution is also very complex. So we can include the voltage stability constraints in the security analysis, and then we can analyze the system behavior. The voltage stability margin prediction and enhancement means you can suppose your system is working fine, means it is stable, it is operating well, but it is prime duty of operator to know that where they are operating, how much margin they are have, and what are the ways that they can enhance the voltage stability margin. with available resources in the system, that is if you are operating the system. In the planning as well, that you can plan some enhancement devices and especially the FACTS controller that can be used, that we can improve the voltage stability margin as well. So the control action planning, that is FACTS controller, special protection scheme, load settings to improve the voltage stability, static as well as the dynamic. So a lot of works already have been done in that area, the load shedding to improve the voltage stability, how that we can have the special protection schemes fast and reliable, so that we can eliminate the area which are having the voltage instability problem, and also that we can use the FACTS controllers, those can enhance the voltage stability margins as well. Another big concern is the voltage stability or any sort of stability. In restructured market, restructured means the power system deregulation, where the electricity is traded and the electricity prices are changing every interval may be half an hour or it may be 1 hour, and it is sold and purchased based on the competitiveness of the biddings of both supplier as well as the consumer side. So this, who is going to take care of the voltage stability? And since your system is dispatched, means you are getting information that how much load you are going to consume and which generator is going to generate how much, and then whenever there is some contingencies are occurring, how that we can take care of the voltage stability concerns in the power system. So the static and the dynamic ATC, reactive power management in the market scenario are also very complex, and that must be addressed so that we can have free and fair electricity market. So normally one paper that came here, that is a final documents, that it is a IEEE PS subcommittee on special publication, and the product number is SP101 PSS, and that came in August 2002, that here the voltage stability assessment concepts, practices and the tools they have suggested, and they have given very good overview as well as the classification of this area. To see this enhancement of these FACTS controllers for the voltage stability, again just one thing is very important for the FACTS controllers. These FACTS controllers are not cheap, so that you can put in each line or you can put at each bus, again which type of FACTS controller you are going to put. There are two types of FACTS controller, one is shunt and another is your series type FACTS controllers. Shunt type of controllers are put on the bus, series type of controllers they are put in the series of the line. There are even the combination of shunt and series. So shunt part is kept on the bus and the series part is kept on line. So as I said, the cost of these devices are very extremely high. So it is not possible to put at each bus and in each line. So we have to decide the suitable location, and if it is possible, the optimal location in complete system. And also I want to mention, it may not be possible that only one device is sufficient for whole system, whole large system. So what you have to do, you have to go for multiple FACTS controllers. Again, you can, it is not that only one controller at two locations, means SBC, etc. Means you can go for a combination of several devices to again to improve your dynamic performance of the system. Dynamic performance includes your the stability and as well as the static performance, that how we can control the power in efficient and reliable manner. So in this lecture I am going to show you one FACTS controller, that is static VAR compensator, that is very popular, and it is basically working in more than 400 locations in whole world system. And this is a shunt device, and just I want to locate first this for the voltage stability enhancement. Then to achieve the maximum enhancement in the voltage stability margin for the system, intact case means base case, and under the critical contingency, just we will see how much maximum enhancement is possible after locating at that bus. Then to obtain the simultaneous enhancement in static and the dynamic. Dynamic, again the dynamic stability is nothing but it is a oscillatory voltage stability margin under the contingency cases. So here again you can see this saddle node bifurcation here, and if your system is loaded at this point, you are operating here at A, then this margin here, this is a, so your AB is your static loading margin, this is a P, and this is your voltage, and your AC is your dynamic loading margin. So always this AC is either less than or equal to AB. This is true. Sometimes this half bifurcation may occur near to the saddle node bifurcation point, so your AC will become your AB. But normally this half bifurcation HB occurs much before than saddle node bifurcation, and then we have the less loading, so the dynamic loading margin is lesser than your static margin loading. Here it is a loading factor, so real power you are increasing. Or you can say if you are using the loading factor, then you have to start from here. If you are loading the P, because earlier you were loaded something and then you are loading here. So if your axis is loading factor, because this loading factor here it is going from 0 to some critical value. So if loading is 0, factor is 0, means you are operating here at the base case. So your A will be here and your this will be AB, is this one saddle node bifurcation, this margin you are having. But if you are using axis at the P, that is a P load, then here you are operating here at certain load, then this difference is your margin. So you have to be very careful what is your axis, whether it is a loading factor or the other load. Now this voltage stability based contingency ranking. The voltage stability based contingency ranking means what we have to do in the power system, we have to rank the contingencies. Again I have discussed about the power system security aspect, where normally we rank the contingency according to the severity. In the power system there may be the thousands number of branches, contingencies, so it is not possible that we can go for all the contingencies. So what we do, we go for some analysis, some sort of that we can rank, and only we have to consider the critical and most probable contingency for looking at your solution methods. So the voltage stability based contingency ranking here has been defined, that is some index has been defined, that is a modified reactive power stability index, security index basically, and that is basically in terms of the reactive power with the no outage, with the branch outage, with the some factor, and then it can be used. So to locate this, what we can do, we can go for this bus static participation factor, and that is your BSPF. Now here you can see what we are doing, this reactive power injection at any bus Qi here, that will be equal to the reactive power generation at that bus minus the reactive power demand at that bus. This reactive power demand can be written as the reactive power demand at that bus in the base case, plus here the lambda, that is a loading factor. If lambda is 0, then we are having the base case starting point, and here we have had some factor, that is how much here your change in this base you are doing and this power factor you are changing, means you can have some power factor change as well of the real power loading. So this is a KDI, some factor we are adding, and this Qi is no doubt here we can write this Qi is a function of your voltage and the delta. Now if you simplify this, here if you are putting QDI here and the Qi here, lambda you are getting a function of a lambda as well, and then if you are differentiating change in the lambda with the QGI here, what you are going to get here, this QGI will coming here and this whole value will be coming here, and you will get one complete here this scalar term, your 1 plus 2 Vi change in the Vi upon del QGI BII, means we have taken one factor here and the remaining we are writing here. So this factor is one factor. Based on that we can send at any particular ith bus, if you are changing the reactive power generation, how much you are changing the loading of the system. If this factor is the highest, we have to calculate this loading factor for all the buses, and then we can get, if it is the highest one, then that location will give your bus static participation factor, means this value if highest, then we have to locate that ith where it is highest, and then that is your suitable location for the shunt device, and that is your static work compensator we have used, but you can also use your StatCom as well. Again for the dynamic, what we can use this bus here participation factor for the bus voltage magnitude can be considered, and this is called your bus dynamic participation factor. Here we have to use, if you are using the dynamic, means you are using the dynamic equation, and then participation factor can be defined again as the left and right eigenvector multiplication. So based on this, what we can do, we can go ahead here and we can determine this your static load margin and your dynamic load margin. To determine this static load margin, as I said, we can use this one package, that is a University of Waterloo power flow. This UWP flow, that is a University U, W for the Waterloo, P for this power flow, power and flow package, that is free of charge and that can be downloadable. And based on that, and it is, as you know, it is working on the continuation power flow method. So you can here, by changing the load parameter, you can get your complete saddle node bifurcation, and then you can get the margin from starting. Let's suppose your lambda is changing here, so from here to this point you can get how much this loading, means you will get directly this loading factor, and you can say you have this margin in the system. So the saddle node bifurcations were obtained using that package. In order to obtain the half bifurcation, again it is a dynamic load margin, just we are going to determine. The loads were gradually increased, means load we keep on increasing, and the differential algebraic equations were solved at each system loading, and here this is the change in your power generation, change in the demand and change in reactive power for the change in the loading factor, and these were used for here as well. So this whole concept just we have applied for 75 bus Indian system. Here this, it is a UPSCB system that we have considered. This area is your, here this is your Obra, here it is Anpra, Singrauli, Rihan, and here is the Panki side, this is a Panki NTPC, Panki here. So this is complete 75 bus. We have only considered 400 kV system and 220 kV system. Again this data is old, presently we have more lines are added here together. So it is a comprising of 100 transmission lines, 114, and then 75 bus, and we are having 15 generators. For this case, what we have done, we have located where we can put the SBC. So the case in that, this we have used this bus hybrid participation factor value for the two most sensitive buses, and here just for the intact case, means for the base case, we found that most sensitive is 44, and the index we found here this. However, for the contingency of, means outage of 29 to 30, this is a Lucknow to one line. Here you can see this 29 here, this 29 is somewhere in this zone, and it is here, the 29 is here and the 30 is here, 30 is here. Yeah, this line is basically a transformer. If this transformer trips, then in that case it is found that this value is this one, and the most sensitive bus is 44. So you can see here, and second one is your 44. So keep on doing the 44, 42, 44, 42, 44, 54. So and also here you can say 44, and we are getting 42. So the most sensitive bus seems out to be 44, and then we have decided that we can put the SVC, that is static var compensator, as bus number 44, and this 44 is nothing but, you can say, where is the 44? 44 is this bus. This is, there is one generation here, and this generation is your nothing but, I think, Auraya gas power station. So after putting at the 44, now you can see how much static loading margin that has been obtained. So we can see the impact of SBC placement on the static loading margin, that is a static loading here. For the intact case, means base case, there is no contingency, no outage. So without SBC, the static load margin is only 0.144 per unit. Per unit again here is 100 MVAs. If we are with SBC at the 44, we are able to go for 1.60, and if we are putting at the 51, here we are getting 173. Although our sensitive case, you can see here we are getting 44 and the 51, but the 51 is giving more, because here you can say this value is more compared to other values. So in this case it is more, so the 51 is giving the most highest, then followed by 44, and we found that putting at the 51 we are getting more. And outage of the various cases we have done here, and you can see for the various outage here we are getting the different values. Here for this outage we are getting 30, here 30, here it is 62, here it is less, here it is 42, it is more, here 48, it is only 22, here 6. So it is basically the most locations, as I said, it is not possible that only one static work compensator is sufficient for whole large system. It may be the two. So we can go for 44 and the 51. But this sensitivity approach is giving idea that these are the buses probable locations, and then you can again go for the actual analysis by putting that SBC. If we will see this voltage profile of the most critical bus here, and that what we are going, it is a no outage, means it is a base case. So you can say without SBC it is your this blue line, and with SBC at 44 this is here. So you can see the loading factor is increased here up to this point, and also here the voltage is improved. Here the voltage in upper, this operating voltage is this much operating. So here voltage is also improved, as well as we are improve the margin as well. Now let us see for outage of line 74 to 73, and this 74 is very big line. This is a Kanpur NTPC to I think Kanpur NTPC here to this line. You can see it from this figure. Here this is a 74, and your 73 is here near to Agra. So outage of this line is very critical, and here if you out this line, now you can see how much change. Here without SBC this margin is up to here 0.02, but if you are doing this you have increased up to 0.05. and however the voltage improvement, you can say there is no big voltage improvement at this line, voltage even though lesser, but we have increased the margin. Now to see the impact of SBC placement on the dynamic loading, we have again done for this various contingency cases here and the intact system, that is a base case. Without loading, here you can say our this margin is 0.149, and here with the SBC at 44 we are getting 0.159. However at 51 there is no increase, and both are getting same. But for the outage here you can say for the various cases this value is higher than this, and then we can say the 44 is the best location for the placement, and also we have increased, we are getting more loading. However, you can see in this case the loading margin is not so substantial, means you can say here the difference is nothing but 0.01 from here to here. I am just calculating. Here it is nothing but 0.021. Here you can say if you are going for 0.02, in this case you are going to 0.028, and in this case you are getting 0.04. So in total it is on 100 per unit base. If you multiply it by 100, so maximum you are getting 4 megawatt. Why it is so? Because this system is highly loaded system, and we have very less margin. It is very critical system, so that loading is not increased much. But still we are improving in terms of your dynamic as well as the static margin here, you can say. Few critical eigenvalues you can see. For the intact system, when the loading was this, you can see this value becomes this half bifurcation, this becomes 0. However, if you are putting in the case 2 where you are putting this value, you are getting this one 0.01. So you can see here with and without here, means this is without and this is with. Now the half bifurcation is improved, means we are half bifurcation, there is no half bifurcation at all for this intact case event. For the outage of this line, again at this loading we found that this half bifurcation is occurring, but at this loading we have, you can say, avoided half bifurcation, and this value is not 0. So we can say that the dynamic as well as the static voltage instability are improved with help of FACTS controller. Correct? कितना हुआ इसमें? 29. So here we saw that with the help of SVC, this half bifurcation point is removed, eliminated, and we at this loading there is no half bifurcation at all, and we can say we have improved the dynamic stability. So we made the following observation with the help of placement for this SVC. A sensitivity based approach for optimal placement of SVC has been suggested to simultaneously enhance static and dynamic stability of the system. Here it is not the security, here we are talking about the stability of the system. The proposed this hybrid participation factors consider the relative weightage of static and the dynamic participation factors based on the severity of contingency from static and dynamic aspect. What is happen? There is a possibility if you are considering only static criteria, your location will be the different. If you are considering the dynamic, then your location will be the different. To have one common location for both static and the dynamic stability improvement, we can have some hybrid, and with the help of some weight factors for the static and the dynamic participation factors has been suggested, and it is again for the base case as well as some contingency cases, because in the base case there is a possibility that your system is you are locating something different location. However, for contingency cases the location, optimal location may be different. So you have to again compromise, and for all the system scenario you have to choose a suitable location so that that can give you a maximum benefit and you can achieve from that location. So the proposed approach for static wire compensator placement is quite effective in static and the dynamic voltage security enhancement. Thus we saw that FACTS controller, the series here, it is not series, it is a shunt, that is a SVC, static wire compensator. So this SVC is called your static wire compensator. Basically it is, we are changing the impedance, and is a shunt device compensator. Another shunt device that is very popularly nowadays people are discussing about, that is a StatCom. StatCom is a function wise it is similar to static wire compensator or SVC, but the StatCom are better, they give better performance than SVC at the several regions, several locations. They are very, very important, but the StatCom are very, very expensive than your SVC. So in our Indian system, even in our UP system, we have one static wire compensator that is near to our Shakarpur station, that is a power grid station, and that is having rating plus minus 280, means we are having 2 units of plus minus 180 MVA, and that is improving your system no doubt very well. Now one is just from very beginning, just we studied the various stability, that is a transient stability, a small signal stability, and also we discuss about how we can improve those stabilities. Now here also just I am going to discuss the practical measures to improve the voltage stability. Again we can improve this voltage stability, again we can divide into the 2 locations. Once just I want to see that if you can do something at the generation and the transmission levels, another is at your distribution level. So here I am talking about the first generation and the transmission levels. The use of reactive power compensators. As you know, the voltage is directly related with the reactive power. So you have to do, if your system is requiring reactive power support, you must provide the reactive power support to improve the voltage and therefore the voltage stability of the system. So the reactive power compensator is must, and the FACTS controllers such as SVC, StatCom, and sometimes the TCSC, although it is a series device, can be quite effective in enhancing static as well as dynamic voltage stability limits of the system. So in the transmission lines you can use FACTS controllers, and also at the generation level you can generate more reactive power if your system is reactive deficit. In sometimes there is a possibility that your system is having huge reactive power, means your, especially that occurs when the loading of the system is less. In that case you have to have reactors, and those reactors must absorb the reactive power during off-peak loads, because the excessive reactive power charging of the transmission line will give the reactive power, and generators are also allowed to absorb the reactive power so that we can have the healthy system. But in most of the cases when the system is peak loaded, or most of the time, we require the reactive power support. So the generators must provide the reactive power support, as well as we have to use the various capacitor banks, FACTS controllers if they are there, again to improve the voltage stability of the system. Shunt capacitors offers economical solution, and these can be used for the preventive application. Try to install enough capacitor banks to operate system generators and SVC near unity power factors. What we do this, again there is a two type of applications. One is the preventive application, another is your corrective applications. So we can use the capacitor banks again for EHV transmission lines for 400 if you are using the capacitors very expensive. So we can go for the lower voltage and we can improve at, especially near to the load, we can put 132, or we can go for the 33 kV bus bars. We can put the capacitor banks, and again we are putting the shunt capacitor. We know the shunt capacitors provide more reactive power support than your series capacitor if you are putting in the line. So in preventive application, try to install the enough capacitor banks to operate system generators and the SVC near to the unity power factor. If they are operating near to the unity power factor, they will enhance the system voltage instability very much. The corrective application includes the fast corrective action within 30 seconds and can prevent instability during the disturbances. If you are having fast corrective action and that you can take action in the less than 30 seconds, then there is a possibility during the disturbances you can prevent the instability. Means you can prevent the cascade tripping of the system, and therefore you can prevent the instability during the disturbances. So that is called the corrective action. In the preventive, already put the enough capacitors so that your generators and the SVCs are operating near to the unity power factor, so that whenever there will be disturbance, they will have the more margin and they can take care of the disturbances. So that is a preventive. In corrective, you have to use the exact value of capacitors so that you can improve your stability, you can minimize the instability of the system during the disturbances. Another application is the emergency application during abnormally low voltage. Means sometimes there is a voltage system is stable, but it is operating very close to the low voltage limit. So we can use the series groups of Y connected capacitor banks can be sorted to provide more Q output, and they can withstand over voltage for 10 to 30 minutes. So we can use some groups of Y connected, that is a star connected capacitor banks. They can provide more reactive power supports, and then we can avoid the emergency situation. So we require the better protection scheme as well, and also the coordination of relays. As you know, if there is a, due to the low voltage profile, if one line or one generator is tripped, then there may be the cascade tripping. There is the voltage will keep on going down, and there will be cascade tripping, and then your whole system may be in the collapse or dark. So the better protective schemes and the coordination of relays are also very important for improving the voltage stability of the system. Now HVDC line controls. If your system is having HVDC lines, as you know, in our UP we have one HVDC, big HVDC line carrying more than 1500 megawatt power, and that is from Rihand to Dadri. It is plus minus 500 kV, that is a bipole operation. So if you can control that power, as you know, we can, main advantage of HVDC that we can control power very efficiently. So we can, more power in HVDC improves the voltage in AC system. If you are dragging more power over the DC line, your AC system will be relieved, and you can load more, and you can have more stability margin. So loading, or you can say controlling the HVDC, we can, loading more HVDC lines, we can improve the voltage stability of the system. But again, if your HVDC line is loaded to its rating limit, so again you don't have margin. Better regulation of generator high side voltage using line drop compensation, secondary voltage control loop about 10 times slower than the primary control loops, optimization of network voltage control to ensure field current limiting of all the generator at a time, optimal dispatch of generator along with the possibility of the fact controllers, and the better schemes and the coordination of relay already I have discussed there. So here what we can use the various other, that is we can use the regulation, better regulation of generators, especially this network side, the high voltage side. We can use the line drop compensator. There is one signal that is used in the exciter that is coming. We can control the bus voltage very far from generator. We can take that signal and then we can set the excitation in such a way that we can improve the voltage of that bus. That is called line drop compensation. So I explained the line drop compensation means you can control the voltage somewhere far from generating station. Normally what happens, if your generator is here, this generator just we feed here the excitation, and that excitation here the field that we get, that is from your terminal voltage here, and we feed here, we can control the terminal voltage. So the exciter is used to control the terminal voltage of this generator. But at the same time what we can do, we can use another auxiliary signal here, that is we can add, and that signal comes from anywhere in the system, and that is called your line drop compensation. Secondary voltage control about the 10 times slower than the primary, because this is your primary control. We can also use the secondary voltage control to improve the voltage of the system, and therefore we can improve the voltage stability of the system. Another is the optimization of network voltage control to ensure the field current limiting of all the generators at a time. You know, because if you can increase the excitation, you can increase more reactive power by increasing the field current. But we have already I have discussed the limiting, I can say capability curve of alternators, that we had this field heating limit. If your current is hitting that maximum value, we cannot operate more field current, because it may damage the field winding, because heat will be not dissipated and that may damage your field winding. So it is called your current limiting, that is a field current limit. So what we can do, we can have a complete coordination of all the generators. It is not that one generator we are keep on increasing the excitation and other generators we are not changing. What will happen, for example, I can tell you, let's suppose here one generator is there and we have another generator here, and this is a complete system, those are connected. If you are keep on increasing the field of this here E, this terminal voltage, suppose you are increasing, what will happen, it will try to generate more reactive power, but this voltage if it is not increased, there is a possibility if it is increased slightly, it may consume the reactive power here. So we have to go for, and it may limit even though your current and the field current. So we have to go for the coordination of all the generators, so that we can ensure the field current limiting of all the generators at a time, and we can get the maximum benefit. We can get the maximum network voltage control with that one, so that we require a optimization problem and we can solve it, and then we can improve the voltage stability of the system, because we will have more reactive power margin, and whenever it is required we can supply during the disturbances cases. Another is to improve the voltage stability is the optimal dispatch of generators along with the possibly fact controllers. Now optimal dispatch of generators, one is that optimal dispatch. Again, optimal dispatch can be delineated into two types. One is your economic dispatch, that is a real power dispatch, and another is your reactive power dispatch. So in the real power dispatch, that we can minimize the total cost. Normally we go for the dispatching so that we can have the minimum cost of generation of electricity. However, this reactive power here, it is related with the real power of generators up to some extent, as already we have seen that the real and reactive power relation of the alternators with this capability curve. So we can generate the reactive power of the system of the generators as well as other devices in the system. Means we have the capacitors, if we are having static var compensators, or we are having other fact controllers, then we have optimal dispatch of these reactive power sources to improve the performance of system, so that we can have more voltage stability margin. So if we are going for that, no doubt we can improve the voltage stability margin by optimal dispatching of generator, and this is called optimal reactive power dispatch ORPD problem, where we minimize, again the minimization may be any objective. Minimization is, you can say, change in the voltage deviation. Minimization may be your change in minimization of the loss subjected to the various constraints. Those constraints are your real power limits. Again, we are not touching the real power limit, because this economic dispatch, that is called ELD, economic load dispatch, is we are here setting the real power generation output. However, ORPD, we are setting the reactive power generation of the generators. So here your objective is the minimum cost of operation. Here objective is the different, that we are changing the voltage deviation, or we are minimizing the loss subjected to the various constraints, and those constraints are nothing but, here the constraints are your reactive power limits of the generators, voltage limits, and also other, let's suppose, FACTS controllers parameter there, then we can have the limit, and then we can obtain the optimal dispatch, and then by that we can have more voltage stability margin, and we can improve the voltage stability of the system. So this is one of the very good criteria, that by that we can achieve that. At the distribution level, what we can do, we have seen this reverse action of the transformers, that OLTC action means whenever there is a problem, because as I said, if you are changing the voltage from one level to another level, there is a possibility that you can land up with the unstable case. To see this, here what I can explain you, let's suppose here this PV curve, this is your PV curve at one tapping, at another tapping you are having another curve here like this. Here if you are operating somewhere and you have changed the voltage suddenly here, let's suppose you are operating here and you have changed from your tapping here from one to this point to this, what happens, you are landing here in this negative zone and your system will be unstable. So you have to block the OLTC action in very severe cases, especially when it is going to act as a reverse direction, means when you are trying to increase the voltage, it is reducing the voltage, and then it is landing in the unstable part of your PV curve. So you can block that OLTC, especially during the emergency cases. Now load voltage reduction can be exercised manually from the control centers. Now this load voltage reduction means you can, if your voltage is reduced at the load buses, you can reduce the load of the system, and that can be exercised manually from the control centers. So what you can do, you can reduce the loading of the system, then you can increase the voltage, and then your system will be more healthy, more voltage instability it will be, means you can improve the voltage stability of the system. Under the voltage load setting scheme, as you know, there are two types of load setting schemes are there. One is the load frequency control, where there's if frequency falls down, normally we try to shut down the loads, few loads, so that we can improve the stability. We can improve the frequency of the system, and that is we are talking about the transient stability. Similar fashion, we can have the relays that if voltage is low and it can set the load, then we can again improve the voltage stability margin. So under voltage load setting can be implemented as a centralized or decentralized stability solutions. Implementation requires proper selection of initiating signals, time steps, and amount of load to be set. So how much time of load, how much load you are going to set, how much time you are requiring for the setting this, so that based on that again you can improve the voltage instability, means you can improve the voltage stability margin here as well. So this is basically a corrective action approach. When you are just leading to that margin, you are very close to the voltage instability margin, then you can take this action. Another is direct load setting. The load setting from the direct detection of the major contingencies, means suppose there is one contingency has occurred that may lead to the severe voltage problems in the system. So with that contingency, if you have any sensing mechanism, and then based on that you can directly trip few of the loads, you can trip it out, then what will happen? It will try to improve the voltage profile, and therefore you can have more voltage stability margin and you can have the improved voltage instability system. Direct load control and the distribution automation, that is a DA, is the communicate emergency conditions to consumers microprocessors by large increase in real time cost of electricity. Thermostatic settings are the load demand then would be changed to reduce the consumption, because here again this voltage stability can also be improved either from the generation end, transmission end, and also it is possible from the distribution end. So in the generation end already I discussed that we can improve the reactive power settings, you can use the optimal setting of the reactive power outputs of generators along with the FACTS controllers. Also we can put some static var compensators or FACTS controller in the transmission system, that will improve your voltage stability margin. But in the distribution side always it is you have to play with the loads as well as the transformer, that is the OLTC. So the direct load control, or you can have the distribution automation system. That automation means you will having some RTU, remote terminal units, and they will sense the system voltage etc. They will give the information to DA system, and that DA system will decide how much load and which are the loads are to be set, and then we can improve your the voltage instability of the system, and can be initiated based on the reactive power reserves of generators and SVC. The DA system, that is a distribution automation system, DAS normally we call, can perform some of the above tasks, that is a serial number 1 and 2. 1 and 2, 1 that was, as I said, it is a OLTC, here it was this, here the blocking of the transformer OLTC action, and that is always we are talking about the reverse action. Second one is this, means load voltage reduction scheme that can be done. This DA system can also prove an effective and the practical method for improving the voltage stability in future, but requires a strong communication between the DAs and EMS. Here it is not only the distribution automation system but also the energy management system. Both must be coordinated, because it is a coordinated system, means how much load it to be set and again how much generation you are having. So all these must be coordinated so that we can have efficient and reliable and more improved voltage stable system. So with this we can now say with the various preventive and corrective actions we can improve the voltage stability of the system. In this lecture we saw the various dynamic as well as the static voltage stability criteria, and we saw the bifurcation for the dynamic and the static, that is a saddle node bifurcation. Also I showed you one example where for a practical system where we put the SBC and that enhanced the static as well as the dynamic stability voltage stability margins, and here also I discussed the various practical solutions to the voltage instability problem. So this lecture basically concludes your whole this module 2, and this now I can recap what we have done from very beginning in this module. First we discuss the capability curve of generators. This is a capability curve, in that we saw the various limiting of an alternator, that is your field heating limits. The various 3 heating limits I derived, and if you remember here I draw, here it is your P, here it is Q. So this is your field heating limit, then we have the armature heating limit, and finally here it is your end heating limit. So this is your capability curve of alternator. I explained, I derived, and then I explained in the detail. Second, then I use the modeling of alternators for purpose of your transient stability, that is a transient stability. We describe this swing equation. Also I describe the equal area criteria for the single machine infinite bus system. I also give some solution approach, numerical algorithm to solve the multi-machine power system, how we can solve, and that is more important that also I describe that how we can improve the transient stability of the system. The transient stability is related with the sudden and the severe disturbance, and then we saw the various approaches, and then I very nicely I explained that the transient stability using the equal area criteria. Then we went for the multi-machine system, and again for the improving the transient stability of the system. Then I explained this here small signal stability, small signal stability. Here in this stability, the sudden but the small disturbance takes place. Then here in the transient stability we analyze with the nonlinear equations, differential equation, but here in the small signal stability we can linearize, and we linearize the system around the operating point, and then we solve and we go for this transition matrix X, and we analyze the behavior of the system. We use eigenvectors, eigenvalues, and the participation factors to go for this, and a small signal stability especially related with the small oscillations in the power system. So how we can improve? Already we discussed some of the modal analysis. We also saw some improvement methods for the small signal stability as well. In this small signal stability, we described that how we can go for the participation factors, what are the roles of various eigenvalues, and then we showed one problem as well for the small signal stability. Another which I discussed, that is the voltage stability. I took almost 3 lectures on that voltage stability, and in this voltage stability, as it is related with the voltage here term, and in this we explained the various static as well as the voltage stability criteria. We also discussed the various bifurcation. I discussed the various methods to analyze the static voltage instability. We discussed this condition number, or you can say singular value decomposition techniques, minimum singular value which I said. We also used the saddle node bifurcation approach. I discussed the continuation power flow techniques, and also the various L index and various proximity index are used for the static voltage stability checking and the enhancement approaches. The dynamic voltage stability, I use the again half bifurcation is one criteria, and for that half bifurcation I have considered only half bifurcation, and then we saw that how and fact controllers are useful to improve the voltage stability. Again, the fact controllers are used for both static as well as the dynamic voltage stability limits. Then I explained how that we can improve the voltage stability limits. Again, at the generator level we can do something, at transmission level, and at here the distribution level, that we can from these 3 angles. Means here we can set the QGs at generation, here we can go for the Q source or some capacitor or static work compensator, here we can go for the OLTC and as well as the P demand if you can go for. So these are the various control measures by which we can improve the voltage stability of the system. So in the total here we discussed starting from the capability curve, modeling of the synchronous machines, then we utilize the transient stability. First I use this classical model where we use the then single machine infinite bus, then I went for the multi-machine system, then I discussed the various approaches to improve the transient stability, then I followed the small signal stability, and finally I discussed the voltage instability where various methods were discussed.